Hello once again from Physics 1053 at Daytona State College. This is Dr. Michael Olson. In Chapter 11, we are going to be discussing oscillations and waves. Here in Physics 1053, we are only going to cover the first half of the chapter on oscillations. The second half of the chapter on waves will be the first topic discussed in Physics 1054, College Physics 2. So we'll begin Chapter 11 here on oscillations, defining simple harmonic motion, looking at what is involved in simple harmonic motion, what it is in the first place, and how it differs from other types of motion. We will talk about the energy involved in simple harmonic motion, as well as the period and the sinusoidal nature of simple harmonic motion. By sinusoidal nature, of course, referring back to trigonometry, we mean the motion that represents a sine or cosine curve. Okay, so let's consider, to start off, we have a block with mass m attached to a spring, as we can see here. We pull that mass out. The spring, of course, is going to pull it back inwards. And as the box moves in, it's going to compress the spring. And when the spring compresses, it's going to push it right back out. And so your mass just goes back and forth and back and forth. This is periodic motion and is the basic motion that we see in simple harmonic motion. Now, assuming that the surface is frictionless, this is going to go on forever and ever and ever. It will never stop. Every time the mass passes the center, which we defined here as the x equals 0 position, this is called the equilibrium point. This is the point at which the spring is completely relaxed. In other words, there is no force on the mass. It's just the momentum of the mass that carries it back and forth. So that x equals 0 is our equilibrium point, and we can measure the force of the spring depending on the displacement from that equilibrium point. And the force of the spring will be negative kx, where k is called the spring constant and is a property of the spring itself, and x is just the distance from equilibrium. Now this principle here is known as Hooke's law. And as I mentioned here, the k is a spring constant, so we don't need to cover any more of that, just a property of the spring. The minus sign in the front is rather significant, rather important. This minus sign tells us what direction the force is. And that minus sign also indicates it is in the opposite direction from the displacement. Meaning if you pull the spring out, give it a positive x, the force will be negative, pushing it back in. But if you push it so it has a negative x, then two negatives makes it positive. You have a positive force pushing it back out. So the minus sign always restores it back to its equilibrium position. Now, a very different point here about simple harmonic motion than anything else we've talked about so far this semester. The force is always changing. Since the position is always changing, the force is always changing, so the acceleration is not constant. Up until this point, we've always assumed constant acceleration, which we do not deal with anymore in this chapter. So, a couple points here. Some we've touched, but others we need to cover. All displacement is measured from this equilibrium point. That's the point at which the spring is completely relaxed. The amplitude is the maximum displacement from equilibrium. We just indicate that with a capital A. And a cycle is a full to and fro motion starting at, say, negative amplitude, going to positive amplitude, going back to negative amplitude. Or you can start at positive A, go to negative A, back to positive A. One full cycle. And the period, as we defined period back in chapter 5, the period is the time required to complete one single cycle. And the frequency was 1 divided by the period, the number of cycles completed per second. Now, if the spring is hung vertically, then of course your spring is going to be totally relaxed, but then put a mass on it that will stretch it to the point where the spring will, or the mass will stop. It will not stretch or compress anymore. The force of the spring pulling on the mass is going to be from Hooke's law. Force is equal to a negative kx, and now x naught being the distance from equilibrium. But that force is going to be completely countered by gravity, mg. So, in this case, the force negative kx is going to equal mg, following Newton's second law. Now, when we do this, when we put a mass on the spring and extend it, this becomes our new equilibrium position. So whenever we have harmonic motion, it will now be measured from this from this position until the mass changes again, and you've got a new equilibrium position. Okay, now we are ready to finally define simple harmonic motion. Simply put, if you have a vibrating system where the force involved in restoring the system back to its equilibrium position is proportional to the negative of the displacement, that is simple harmonic motion. So in this case, Hooke's law says that F is equal to negative kx, so the force is proportional to the negative of the distance. So this is simple harmonic motion. Once it's oscillating, we'd simply call that a simple harmonic oscillator. Let's take a quick look at the energy of simple harmonic motion. We've actually already seen this a little bit back in chapter 6 when we talked about energy. Back in chapter 6, we defined gravitational potential energy as mgh, but we also looked at the potential energy of a spring as 1/2 kx squared. Again, this k is the same k we saw in Hooke's law. That is the spring constant, a property of the spring. So in an oscillator, you have both potential energy from the spring being stretched as well as kinetic energy from the motion. So the total mechanical energy will be kinetic, 1/2 mv squared, plus potential, 1/2 kx squared. Just like with the other energy questions we dealt with in chapter 6, mechanical energy will be conserved as long as we assume a frictionless system. If we have friction, then we have non-conservative work, and that negates the conservation of energy law. Okay, so let's consider a spring where you have compressed it to its maximum position, negative A, where A is the amplitude. So we have complete potential energy at this point. And potential energy is 1/2 kx squared. In this case, x is the amplitude A, so our energy now is 1/2 ka squared, as we defined here in this equation. Now, as we let go, the mass will move forward, gaining velocity, losing potential energy, and so when it reaches equilibrium, our potential energy is completely gone since x equals 0. Our energy is now completely kinetic. The mass will continue to stretch, and as it does so, that kinetic energy is converted back to potential energy, and our energy is once again 1/2 ka squared once it reaches its amplitude again. And then at any point in between A and 0, your total energy will be 1/2 mv squared plus 1/2 kx squared. So, the total energy of the system can always be written as 1/2 ka squared. Always. because k is the spring constant, that's not changing, and the amplitude, assuming a frictionless surface, will always be the maximum distance from equilibrium. So those two numbers will not change. So we can say that since energy doesn't change, the energy at any point x is going to equal 1/2 ka squared. Now if we solve for velocity here, then we get this series of equations. We get that the maximum velocity is going to be the amplitude times the square root of k over m, and the velocity at any position x is going to be plus or minus that maximum velocity times the square root of 1 minus x squared over a squared. And these equations can always be used in any simple harmonic motion. Now let's take a look at this example where we have a simple harmonic oscillator moving in a circle in x and y. This gets to be kind of complicated because the object is always a distance a from the center. However, if you look at this from the side, what you will notice is that as it moves around the circle, in that motion I just indicated, from the bottom of the circle to the right up to the top of the circle, what you will see from the side is it will just move to the right to your maximum amplitude A, back to the center. And then as it continues its motion from the top of the circle back to the bottom of the circle, you will just observe it going to the left to its maximum amplitude, back to equilibrium. So really the circular motion is a type of simple harmonic motion and will follow the same laws that we saw here. So we can use the period and the frequency to define the properties of the motion, of simple harmonic motion, if we go through the definition that we had earlier in chapter 5, that the period would be 2 pi r over the velocity, and then we take our definition of velocity and plug that in, then our period turns out to be 2 pi times the square root of the mass divided by the spring constant. And of course, frequency would be 1 over that, which would be 1 over 2 pi times the square root of k over m. Now, it is very important to point out that in this case, we're talking about m being the mass on the spring, but the spring itself is considered massless. If the spring has no mass, then this equation works perfectly. If the spring does have mass, then that does change a little bit, and that is more of a realistic example. For the sake of this class, we will assume massless springs. Therefore, we can follow these equations here on this slide. Now, imagine you have a mass on a spring oscillating up and down, and you have a paper behind it that is moving along. The mass can trace a pattern that actually looks exactly like a cosine. So we can describe the position as a cosine function. The maximum position would be amplitude, and the cosine function would be omega t, where omega is your angular velocity times t would be your angle theta. Another way to write your angular velocity is 2 pi times the frequency, or since frequency is 1 over the period, you could have it a cosine 2 pi of time divided by period. Now, simple harmonic motion could start at any point, so we could start our harmonic motion starting at 0 and continuing from there, and it would just look like a sine function. And so it's the exact same function, just shifted by a quarter of a period. I'm out of time for this video, so I will come back in the next video and we'll discuss this, start from here, talking about velocity and acceleration as cosine and sine functions.